experience in the industry and has worked in companies like Xilinx and Blackmagic Design before. This lecture consists of two parts. The first part will be a general introduction to the IC design industry and how life will be as an engineer in the industry. And the second part will be rather technical, which talks about cache coherence mechanisms. Okay. And before I welcome Mr. Timothy, let me also welcome Hoyani, who is his spouse, and who also happened to be in all the modules that he's doing. Okay, so yeah, let's put our hands together and welcome Mr. Timothy to give this lecture.
Just a little bit about me. I think Dr. Rajesh really mostly covered it. So I'm a senior archaeology engineer with Marquis Semiconductor. Actually, it's a Silicon Valley startup. We have slightly less than 100 employees currently. Right? So as you mentioned, we're doing fabless IC design, and I'll go more into that of what exactly is termed as Semiconductor. So currently we have 4 sites around the world. One in Silicon Valley, so one in India, one in the Philippines, and Singapore's most recent site. But before the end of the year, we'll be also opening a site in the Netherlands. So, yeah. Yes, and so there's my contact email. If you have any questions, we'll first my emails. Oh yes, and as Rajesh mentioned, I'm a former student of CG3207 for my USPC alumni. So I feel very honored to be invited back to this meeting. Right, so as mentioned, we'll be doing some industry sharing, right? And I'll mostly be talking about digital IC design, because that's the part of the field that I do. And also I'll be maybe sharing more about my own experiences in the career, right? And something will take us until the break time. And after that, I'll be doing maybe half an hour of the on some industry applications of cache coherence. Then let's go into part 1. So firstly, semiconductor industry. That is the larger industry that I work in. But it's probably a term that some of you might have heard about, but I'm not very sure about. So maybe I'll quickly go through it. As you all should know by now, a semiconductor is a material which has a conductivity value between that of a conductor and an insulator. So common elements involved in semiconductors would be like silicon, most famous one, also germanium and gallium arsenide. Right? What's interesting about semiconductors is that through a process called doping, we can modify it to create materials with variable electrical properties, such as if the electrical properties vary according to changes in the environment, we can build sensors out of those. Or for example, if they can emit or detect or control light, we will call those, we could build optoelectronics from them. And maybe most importantly for us, right, in this module, would be that if we can control the amount of current that flows through them, we can build circuits out of these materials. Now let's look at the semiconductor industry in 2021. So it's actually worth about 550 billion, and this is how it breaks down. Right, so as I mentioned, sensors, optoelectronics, but the vast majority of it is actually circuits. So the difference between discrete circuits and integrated circuits is that for integrated circuits, we have like hundreds of thousands, maybe even billions of these little gates and transistors on a single piece of semiconductor material. So we call it integrated. And especially pertinent to the students of CG3207, where we learn about processor architecture and also about digital design would be, what we call the micro integrated circuits, so that covers like microprocessors, microcontrollers, and also the logic IC. As you can see, it's actually quite a big percentage of the entire industry. Right? So, what you guys are learning is actually very relevant. So let's look at the semiconductor industry with relation to the whole global economy. As I mentioned, it's worth about $500 billion in 2021. However, this might actually seem quite small compared to a global economy that is close to 100 trillion. Right? So that's like 0.5%. So can we really say that semiconductors are important? We can. The first reason why is because semiconductors, the chips that the semiconductor industry produces are critical in other basic industries, right? For example, let's say industrial automation. So industrial automation will then be critical for many other industries. And some of these industries, and of course the semiconductor chips are also used directly in all these industries, right? So in automotive, right, a market which is worth about $3 trillion, especially in electric vehicles, advanced driver assistance systems, radar, cruise control, stuff like that. Also the tech industry, which is estimated about $5 trillion nowadays. The tech industry wouldn't exist if you didn't have computers, servers, data centers, stuff like that, all of which use computer chips. Telecommunications, so I'm giving this presentation also through Zoom. That's simply not possible without the internet, right? And of course, the internet runs on our chips as well. Things like consumer electronics, I see all of you guys with your phones, with your laptops, right? So these are all part of consumer electronics. Also important, aerospace and defense, right? So, right now, with what's happening with Ukraine and Russia, so like Russia cannot build its advanced weapons because the weapon chips there's been a ban on exporting chips to them, right? And the list goes on and on. So you could even just see how important it is with a simple just thought, right? Just try and imagine your life without any form of electronic device. And that's how important the semiconductor industry is. So with that overview of the semiconductor industry, now let's talk about the digital IC design process. Yeah. So as I mentioned just now, it kind of covers the logic ICs and the micro ICs. We can think of the digital IC design process as being split into a couple of logical stages, right? And we roughly classify them into 3 parts, called front-end design, back-end design, and manufacturing. I'll go through the stages in detail now. The first stage in front-end design is what we call specification or architecture stage. So what is this stage about? In this stage, we gain an understanding of the behavior of the circuit that we're trying to produce in the end. And sometimes we call this the behavioral level of the circuit. From there, we move to the second stage, also known as RTL design, also known as microarchitecture. The goal of the microarchitecture stage is to transfer that behavioral level specification into a register transfer level, also known as, that is RTL. Right? This is also known as the functional design step. Right? So basically through things like Verilog code, VHDL code, we are describing the function of the circuit. And of course, we cannot have functional design without functional verification. And the goal of the functional verification step is to ensure that the functional design is working as specified in the first step. From there, we move to the starting of the back-end design. And it's called synthesis. So synthesis basically takes that register transfer level circuit, right, and it specifies it down one level or up one level, depending on how you see it, into what we call the gate level, right? So now we have a net list which consists of all the gates comprising the circuit and how they are connected. And it should be noted that at this point, we will then conduct further gate level simulations to ensure that the circuit at gate level still functions correctly. If it does, we can move on to the physical design step. And this is basically the last step before manufacturing. So what we do is we take that gate level circuit and we move it down to the final level, which is called transistor level. Right? This has many names in the industry. Sometimes we call this the GDS2 layout file. Sometimes, people also commonly refer to this step as when it's completed, it's called tape out. Right? We say the chip is ready for tape out. Right? So these tape out files will then be ready to go to the manufacturing step. The first step of manufacturing is called fabrication. So, quick disclaimer, I don't really work in the manufacturing side, right? So, I won't go too much into detail in it, right? It's actually, in and of itself, an extremely complex process. You know, there are more than 1,000 discrete steps involved in manufacturing the IC, right? In fabricating the IC. And it involves some of the, literally some of the most advanced machines in the world. But, I will not go too much into that. Suffice to say that the output of this fabrication step is that we will have the completed circuit chips on the semiconductor wafers, right? And this will be tested at a wafer level. The last step of the manufacturing process is basically called assembly and test. So the first step will be something called die saw, which is where the individual little computer chips are being cut out from the wafer. Then these will be packaged, final testing will be done, and then they will be ready to go into whatever end product they're testing for. Right? And so these are you can think of this as the 7 logical steps of the digital IC design process. Having looked at the steps of the process, maybe now we can look at what companies are involved in this process. The first group of companies would be what we call the fabless companies. So this is a term which I mentioned in the introduction briefly. Fabless means that these companies are involved in the design, right, all the way up to the back-end design, but they don't really they don't really participate in the manufacturing and the fabrication of the chips. They will outsource the manufacturing to what we call the pure play foundries. Right? So these pure play foundries only work on manufacturing, broadly speaking. Yeah. Some famous fabless companies would be like those, the 6 at the top. These are American companies: NVIDIA, AMD, Xilinx, which recently got acquired by AMD. Marvell, Qualcomm, Broadcom. Then there are also some very famous Taiwanese companies like MediaTek and Realtek. HiSilicon is a very famous Chinese fabless company. And of course, the company I work for is also a fabless IC design company. Under the pure play foundries, there tends to be far fewer of these companies, right? But the famous ones would be like UMC and TSMC from Taiwan. SMIC would be from China, and Global Foundries is US. So there are actually companies which do both the design and the manufacturing steps. We will call these the IDMs, integrated device manufacturers. On the right there, you can see some European companies like Infineon from Germany, ST Micro, which I think is a Swiss company, NXP from Netherlands, I think. The center we have American companies, Intel, TI, Micron. In the last column, we have South Korean companies, SK Hynix, Samsung. So, supporting these companies in manufacturing their chips and designing their chips, we have other companies also. The first category would be EDA companies. EDA stands for Electronic Design Automation. So these companies actually build the tools that are being used in various steps. For example, to verify the circuits, to do the synthesis, the physical design. Yeah. There are 3 very famous companies in the EDA space for IC design, called Cadence, Synopsys, and Mental Graphics. All 3 of these are US companies. Supporting the manufacturing steps would be a couple of companies that make equipment, and some of the most famous ones would be ASML and Applied Materials. having looked at the companies, some of the more famous companies in this space, maybe let's look at some of the commonly, some of the terms you will commonly find, when it comes to like job roles in this industry. So in the specification or architecture step of the process, some common terms you will find are like system architect or performance modeling. In the RTL design step, typically there will be a combination of these kind of terms. So digital design, IC design, ASIC design, silicon design. Under functional verification, we have typically we shorten this to call DV, so DV architects, DV engineers, and then we also have FPGA prototyping engineers. The synthesis and physical design steps tend to be performed by the back-end team, as we call it. And in this back-end team, you have people like the layout designers, the physical design engineers, P&R engineers, implementation engineers, DFT engineers. DFT actually stands for Design for Testability. So these are the guys who are responsible for, after the chip design is done, they'll be adding on additional circuitry so that the chip can be tested after it's produced. So for fabrication step, these are some general terms, right? As I mentioned, I'm not too into that section of the industry. Some common terms would be like process engineer, equipment engineers, quality engineers, manufacturing engineers. And lastly, for assembly and test step, some terms you might find would be like the validation, the characterization, test engineers, and packaging engineers. Alright, so lastly, let's talk about how the module that you guys are taking, how it actually maps nicely to the steps of the digital IC design process. Firstly, as you might be able to guess, we have the specification step, and that is where you guys are learning the ARM processor step. Yeah, so through the lectures, it's being described for you how your processor should be behaving. So RTL design step, right? So you have to take the behavioral specification and translate that into functional design. So through a process of working with let's say the framework and skeleton code provided during your labs, right? You'll be working on various modules to bring up the whole design. And of course, together with that, you guys have to do your test benches, right? Running your assembly code in the simulation. Because you guys are implementing your processor on FPGAs, so the synthesis and PD step tends not to be so involved, right? To you guys, it's mostly almost like a 1 or 2 button click kind of thing. But the idea is still the same. The functional circuit is being broken down into the physical resources on the FPGA, for example, the NUTs, DRAMs, registers. And so for the same reason, we don't actually have a fabrication step in CG3207, but you do kind of have your assembly and test step, in the sense that after the bit stream has been programmed onto the FPGA, right, then you can do like kind of like post-production testing of the circuits, right? Seeing if it behaves according to spec. And if it doesn't, then you go back to your RTL design step. Right. So actually, this module is pretty much a microcosm of the digital IC design industry. Alright, so that brings me to the end of the industry kind of overview. So before I continue on with the sharing about some details about the digital design career, I thought it might be interesting to do a little Kahoot poll of you guys to kind of get some idea on your opinions on some things. So So I guess most of you guys should be familiar with how carbon works, right? So if you all could join the survey. So just wait for a couple of minutes. Survey. Okay, I think probably can get started. So basically, this will be a couple of questions to kind of get you guys' views on some career-related matters. So for this one, it's multi-select. You can just choose as many options as you think are suitable. So it's basically just trying to understand, the students of CG3207, what kind of careers are you actually considering? So I think maybe not very surprising. I kind of expected that there'll be quite a few software engineering people, data science also. But I think it's quite heartening, right, to see that quite a few of you are interested in the IC design and also the semiconductor industry. So I'll definitely be talking about this in more detail later on. So let's move on to the next question. Okay, so again, not very unexpected, sort of. But I think we can see that most people find it to be at least quite an important factor, right? This question is about, let's say, after your undergrad, would you be willing to pursue a master's or something to enter a career?
Actually,
Okay, so yeah, actually I have to say this one surprises me a little bit. I would have thought more people would be on the kind of in between, right? But okay, it's very interesting. So I think this one is something that I think most of you all kind of consider nowadays. Alright, so again, not really surprising. In this post-COVID era, we've kind of become accustomed to flexible working locations and hours as kind of the norm. So the last survey question. So it's kind of talking about, how high you want to rise in your career. Okay, so yeah, it seems like a lot of you, basically you all want to rise to that high level. But I guess it's quite interesting that we have a couple of people who kind of see it as a not important. Okay, so the last question in this Kahoot will kind of be a quiz question, okay? Which I just want to get you guys a sense of your guys' opinion on that thing. So let's have a look at it. So, what do you think is the median gross yearly income in 2021 of degree holders, right, between the age of 35 to 39? In Singapore, yes. So this means that it's before you deduct your employee CPF and income tax, but it covers everything. Your bonuses, your OT, commissions, everything. So all in, what do you think is the yearly amount for degree holders between 35 to 39? Okay, so I can't say this was unexpected. So actually the amount, the yearly amount, right, of degree holders is not as high as you guys might think. And the reason why I talk about age group 35 to 39 is because actually this is what we would call a mid-career level, right? So you all start your careers at around age of 24, 23, 24, 25, something like that. So after about 10 years, you guys will be at this age range, starting this age range. So I'm trying to get an understanding of what you guys feel like you should have achieved by that time. So, okay, so I think that concludes the Kahoot quiz. We'll return to the presentation now. Alright, so now let's return to section 2. Right, I'll be talking more about career and digital design. Alright, so firstly, as you guys kind of indicated, right, so the software development or engineering careers, data science are actually of quite interest to you guys. So I wanted to kind of share my perspective, being inside the digital design industry, how I kind of see some of the similarities and differences between digital design and these careers. Right? So let's kind of take it from the top. So firstly, work life. It's actually quite similar, right? In digital design or any of the other two careers, you basically work from a computer. So remote hybrid is quite common. And you are working kind of like on a project-based, deadline-driven kind of schedule. Right? So you can manage your work hours. You want to work late at night, early in the morning, whatever. It's pretty much up to you, as long as you meet the deadline. Now let's talk about the labor pool. By this I mean, who are the people that are going to be kind of competing with you if you choose to enter into these careers? Let's start with digital design. Typically speaking, at a minimum you need like a EC or CG degree, right? And in terms of higher education, right, there is an advantage, but it's not really a big one. So typically it's not required that you have a master's to do digital IC design. That's point one. Secondly, if you do have a master's, it typically just gives you a 2-year so-called discount on the required years of experience. So let's say a position is looking for a 5-year experienced engineer. If you have a master's, it will be master's plus 3 years. In terms of software engineering or development, it's even more to that side of not requiring postgrad and stuff. So it's a good career for people who are totally not wanting to do postgrad, right? Why I say it's a formal degree is not quite as necessary is because although typically the software engineers would have at least a bachelor's degree, but you also have some proportion of them who went through, let's say, coding bootcamps and stuff like that, or even they are self-taught. On the opposite end of the spectrum, we have the data science side. So of course, data science is a very wide term, okay? But typically the people that you would see going into this industry, many of them come from quantitative degrees, right? For example, stats degree, econs degree. There are also quite a few specialized programs specifically aimed to produce data science employees. For example, the School of Computing's Business Analytics program. And also, because data science tends to be a more technical kind of field, right? So masters are quite preferred. And also there are quite a lot of PhDs who enter into this field. So it's just something to take into account when you're choosing a career. Who are you actually competing with? Let's talk about labor demand. Now, it is true that, let's say, if digital design has X number of jobs, the software field actually has an order of magnitude more jobs, right? So something like 30 to 50 times jobs. Data science has also quite a few times, not as many, but let's say it's also 3 to 5 times. So again, just some factors to consider. Do you want to go into an industry where competition might be fiercer, but there's also more places? Or you want to go into an industry where you are more suited to going, but also fewer places? It's kind of a personal kind of choice. Change in the state of the art. Now what this is kind of talking about is on a pragmatic level, practical level, how much time are you going to have to spend during your career keeping up with the latest stuff in the field, right? So definitely on the digital design side, because it's very engineering focused, it's basically you can say that it's slow, right? We don't have new things coming up every year or so, right? For example, the latest HDL, the system Verilog, and that came out in 2005. Before that, it was Verilog in 1985. So you can kind of see the time spans that we are working with here. And certainly, software development will be moving much faster. Right? You'll be maybe needing to learn new libraries, new frameworks in the matter of, let's say, years, at least, right? And for data science, because it's such a new field compared to software development and even digital design, so the rate of advancement of the field is even faster. Right? I know people in the field, and basically, quite some proportion of their time is spent reading papers, keeping up to date with the latest. Job responsibility variance. So what this means is, if you go for a career in this field, what you are expected to do on the job, is it quite standard or is it going to vary a lot? As I kind of mentioned just now, in data science, it's quite a broad range of things. You could be doing things from, say, from the business analytics kind of stuff, right? All the way up to like AI, machine learning, modeling, this kind of stuff. So it's a big variance. Whereas in software development, digital design, you kind of know what you are getting or what you have to do if you go into the field, basically. It's not about upwards mobility. Yeah, so this is kind of my take on it, right? That in the engineering fields, digital design and software development, I would describe it as we have a well-defined career ladder, right? So the companies basically have not exactly standardized, but quite common set of levels of engineers, like junior engineer, mid-level, senior, staff engineer, principal, stuff, something like that, right? And when I say it goes all the way to the top, what I mean is that there are very clear pathways by which an engineer can rise up to, let's say, VP of engineering, or even to, let's say, the CTO kind of position. So it does go all the way up to the C-suite of the company. I think partly because data science is such a new field, so, and also because the job scope tends to be quite varied. So we tend to just have a couple of more common positions. Let's say you start off as a data analyst or data scientist, then you become a senior data scientist, then maybe become a data manager, and then after that, it kind of becomes quite vague and not very defined. Right? And also, as I mentioned, because it's so new, so there's not such a clear pathway by which someone could rise from, let's say, data science manager and go into one of the VP roles or even in a C-suite. Of course, this might change, in let's say the coming years as it becomes a more established field. But currently, this is how I see it. Lastly, let's look at the tedium or unengaging task. So for this, it's basically while doing your job, how much of the time do you have to spend doing so-called boring stuff, like stuff that you might not be doing? I'll talk more about it later. But basically in the engineering fields, there's not so much. In data science, I think the biggest part of the tedium stuff tends to be the data processing and data cleaning steps. Yeah, which typically take up a very significant proportion of a data science program. So now, let's say you want to go into a digital design career, right? And you might want to know, what kind of company should you join. So here I will share some of my personal experiences. So disclaimer, this is not meant to be any kind of definitive statement. I'm just sharing what happened to me, the way I see things. The first thing we might look at is, you want to join a big company or a small company, right? One thing we can consider is the rate of growth. It should be quite obvious, right? So a small company definitely has the potential to grow much faster than a big company. This is just how it works. And how rate of growth affects you in your career is that if the company grows faster, you have more chances for promotion, for advancement, salary raises, things like that. Let's look at scope, responsibilities, and learning opportunities. So again, I think this is also should be kind of obvious. In a big company, your work will typically be quite specialized. You'll be in one team which focuses on one thing, for example. Right? And it's definitely not easy for you to move out of one team and join another team doing something else. So in that sense, you won't have so much opportunities to learn different things outside of your particularly well-defined scope. Whereas in a small company, so first point is that small companies typically require their employees to take on a variety of different roles. Right? And secondly, it's typically easier to move around within a small company to different teams. Third is something I would term as cog in the machine. This kind of relates to how big companies kind of have a quite deep hierarchy of employees, and how it can lead to kind of like an impersonal kind of So, for example, back when I was at Xilinx, which is definitely on the scale of a big company, right? Very big. I think in my 2 years there, the highest level of management that in the company that I managed to meet personally, and it was just at one time, would be 3 levels above me. So my managers, directors, director, right? So like a division director, something like that. And that was like just visiting for 1 day, half a day, something like that. And we just had like one meeting. The whole team had a meeting. Right? And you know, he's also at a level where he's still like 2 levels below the CEO. So when you're in a big company, because of the hierarchy, the upper levels of management would tend to be like, you know, they might as well be not real in a way. Like you don't personally get to interact with them basically. Whereas I can contrast this to my time at Marquee, for example. So because the hierarchies are so flat, right? There's maybe like 3-4 levels, for example. You know, in the first 2 months, I already had several personal like talks with the CEO and other people at the level. So in a big company, you might feel like you're just this one small part of an entire huge organization, and you don't really matter in a way. Whereas at small companies, you tend to know more people tend to know you. There's less of an impersonal kind of feeling. Let's talk about internal equity. So internal equity is a term typically used by HR in companies, but you guys can think of it as bell curve. Is anyone not familiar with the term bell curve? So I'm not saying it's exactly the same thing, but it's kind of analogous. Okay. So in a big company, it's kind of like you being a student in a module with a large cohort, right? So people are graded according to the bell curve. You might think that you did very well on your midterms, think you did very well in your projects, for example, and then final results come out, and you find out that you got like a B. So the reason that happens, of course, is because you are being graded not in an absolute sense, but in a relative sense, relative to everyone else. You're being benchmarked against them. Right? It's kind of like that in a big company. Right? So internal equity is kind of the term for like, being fair to all the employees. Right? So for promotions, for salary raises, things like that, you're basically being benchmarked against everyone else in the company. Right? So sometimes you might feel like you're doing well, but you're not being rewarded like what you would expect from what you're doing. Whereas in a small company, you can kind of think of it as being in a module with a small cohort of students where the prof doesn't apply the bell curve, right? So then there's a much more direct relationship between the effort you put in, how well you did at the midterms, the project, and at the end, you pretty much know, right, that whether or not you're going to get an A. So it's kind of like that in a small company, where there's a lot more scope for you to directly correlate, the efforts that you put in to your final rewards and compensation. Okay, stability or lack thereof, instability. So we would definitely say that big companies are stable. But is that always a good thing? So it's a good thing if you kind of like working in that kind of environment, right? If you like clocking in at 9, clocking out at 5, you always know what you have to do, you always know what's going to come up next, where you don't get disturbed from the day-to-day routine. Big companies are, then you want to go to the big company. But if you're the kind of person that likes to push change, to drive proposals, you have ideas and you want to see that benefit the company. In a big company, there'll be a lot of processes and people that kind of stand in your way that you have to get to, to push change. Right? Whereas, again, using a personal example, so the fact that I'm standing here right now, giving a guest lecture to you guys, right, is because wrote a proposal to the CEO, right? I said, for purpose of campus hiring and reaching out to students, I want to give a guest lecture. And CEO, said, okay, that's a good idea. Then he approved it and allowed me to use some of the company timeline to prepare the lecture. So in small companies, it's like that. You'll be able to know who are the people you need to reach out to push through certain proposals and changes, and you can leverage on like personal connections with them to see it go through. Lastly, let's talk about processes and methodologies. It kind of relates to the previous point. So in big companies, typically you have more well-established processes and methodologies. Again, it's good if you want to learn from them. But if you're the kind of person who might enjoy, say, defining and giving new processes and methodologies for the company to follow, then a small company will be better for them. So now I'm going to maybe give a personal suggestion in a way, and you can just take this as what I might have told myself 5 years ago. When you're starting out, I would think that it's a good idea to join a small company with two important caveats. One is that as far as you can make sure, it's a company that has good growth prospects. Right? So this links to point one, the rate of growth. And secondly, you would want to make sure that you have experienced people that who can mentor you so that you can grow. Right? And after, let's say, 5 years, you've grown a lot at a small company, you've learned a lot, right? Then I think it makes more sense to me for you to then, if you wanted to, at that point, you could move to a bigger company, because then you would have a lot more leverage to negotiate your position and compensation at the big company. Right? Because when you're just starting out, I mean, what can the big company use to evaluate you anyway? At most, first class honors, second class upper, something like that. Right? It's not, I mean, you basically don't have much room to negotiate with them and say, I want a higher pay or a higher wage. Right, second kind of comparison we might look at is multinational versus local companies. So it tends to be the case that multinational companies would typically give better overall compensations and also benefits. It just tends to be the case. There's also an interesting opportunity for, let's say, if you want to work at a different side of the company. Let's say you want to spend a year or two working in the US, for example. You might look for a company that's headquartered there. And they will do things like sponsor or work visa and stuff. And also, in a multinational company, you will be usually working with teams around the world. Right? So sometimes that can be a kind of a negative thing. You have to have meetings with your boss in like 12 hours difference, and then you'll be at late in the evening or something, or really early in the morning, right? But also it can be quite a good thing, right? Because we have to meet different kinds of people, we have to work with them. So overall, I would say most of the time it is better to look for a multinational company. And lastly, a little bit of company culture. So previously I mentioned that in a digital design career, typically you can do like remote or hybrid work and also have flexible working hours. I just want to mention that this is not always the case, and you will have to make as sure as you can before joining the company, right? That you actually know how it is like in the company. Because there are some companies out there who are more rigid about things like working hours, and they prefer their employees to come back to the office and work from home. So just ask seniors who are there, or read reviews of Glassdoor, something like that. Just try and make sure you know what you get into. Okay, so that was kind of some of the considerations that you would want to think about when you're choosing a career, choosing a company. So now I'd just like to talk a bit about, personally, what are the 3 factors that I kind of, how I view my current career. the first and most important to me is actually the factor of enjoyment, right? So this is talking about, do I enjoy my job? And the fact is that working as a digital design engineer, I can say that it's an extremely engaging and challenging job. So it's engaging because at all steps of the design process, when you're reading the architecture, for example, when you are doing RTL design, even when you are doing debugging and verifying, there doesn't really come a point where it becomes some kind of steps where you can just switch off your brain and it's mindless work. No. At all steps of the process, right? Everything that I do, basically, I have to be 100% that working on it. And the challenge part of it comes from the fact that you're building stuff. You're building stuff that nobody else is building, right? And people are trusting you to build and deliver this thing, right? So you're being challenged in a way that you personally have to deliver the designs, right? You have to understand the specifications. I mean, especially at my level, no one's going to help me understand the specification, right? I have to read it myself. I have to personally ensure that what I understand from the specification is correct. I have to do RTL coding myself, do the verification and stuff like that. Right? So, suffice to say, if you like a challenging job, digital design is definitely for you. So, kind of linked to that would be satisfaction and achievement. So, for example, I'm sure you guys have also felt it, right? As you go through the labs, when you have completed your RTL design and it passes the test benches, it's that kind of feeling, right? Maybe multiplied a couple of times, because finally seeing that design which you took so long to do, right? And you sweated over it, you standardized over it, and then finally it passes the test cases. That is the feeling when I'm talking about achievement. And also satisfaction comes from, say, earlier I mentioned that we have the design verification step. So typically these are performed by DV engineers, right? So for example, my designs would, after I have run some kind of body level testing on the unit test, they will be passed to the DV engineers to run a much more comprehensive suite of tests, right? And so typically they will find bugs in your design because they're running all kinds of tests on it. But then you slowly clear the bugs and your design progresses closer and closer to 100% bug free. And when it's finally done, you will get the sense of satisfaction. So, slightly less important factor to me, but also very important, would be what I call value-based design. And I think I kind of alluded to this in my introductory slides, right? I really enjoy working in an industry where the products I build will be used. It's not an exaggeration to say that they form the foundation of modern life, right? They could be chips that are going to be used in future computers, mobile phones, other stuff. But one thing I found quite cool also, about working on products which then go into, let's say, consumer products and stuff like that, is that what the consumer sees is one generation of a product, but the designer will typically be working on, let's say, 1 or 2 generations ahead of the product. For example, let's say the latest USB is, let's say, USB 3 or something, right? So, when I was at Lec instead, when USB 3.2 was a product material for consumers, I was already working on USB 4. So there's that kind of factor of seeing that you are actually on the cutting edge of technology. Okay, so the last factor, as a lot of you have already demonstrated, is of course I also find compensation to be very important. I would say that in a digital design career, it is, honestly speaking, it is not for the people who find compensation to be the most important. Because it is not the job where you will achieve the highest level of compensation. That being said, you will most likely achieve a very comfortable standard of living with the compensation that you get from a digital design. To be more specific, slightly more specific, I will give some estimated numbers now. So, in your early career, starting out, you might expect something on the order of say 4 to 5K as a starting salary, like basic starting salary. And so by mid-career, and here is why I was asking you guys to kind of guess what is the 35 to 39 age median annual income. So by mid-career, you will probably start to see your total compensation in a year reach around the 6-figure number, 100K, right? And after that, in your mid-career, although it will definitely depend a lot on your personal ability and also on the kind of opportunities that you get and also how well developed your network is. Definitely on both the individual contributor track and the management track, it is possible to be reaching annual GC of let's say 2 to 300,000. And just to provide another reference, the median income in Singapore is about 50,000. So you can see that this is actually a very decent and comfortable kind of compensation range. Okay, so next I'm going to show kind of like a little cross-section sort of the job market. So these are some screenshots that I took from the website, the job portal called mycareersfuture.gov. So can I just get a show of hands? How many of you all have heard of this job portal? Okay, so I can see most of you all don't know it, and I would highly suggest that you guys go and see this. One reason being that it is the only job portal where companies are mandated to put the compensation ranges together. Right? So you get information from there which you can't get otherwise. So definitely go there and get it. So yeah, maybe we'll look at on the right hand side here. So these are entry level jobs. So jobs which don't really require you to have experience. On the top, you can see a job from Realtek that is doing IC design, in particular IP development. So, and below that you can see a job for FPGA, right? And it's actually a research support job. And that one's from NTU. So these are just a few examples that I saw on the job portal a couple of weeks ago. So in the middle, will be another IC design job. This time they call it silicon design engineer. But as we saw, this basically just refers to the RTL design stage. Yeah. And it's looking for someone with, let's say, 2 years of experience and above. Right? So kind of like a mid-level engineer, something like that. And on the right, again, we have 2 different kinds of jobs. So firstly would be the one from Marvel. And so there's a senior engineer for digital IC design. Yeah. He's looking for about at least 4 years of experience. So you can see that. And below that would be something quite interesting, which is FPGA HFT engineer. So HFT actually stands for high frequency trading. So people who work in this kind of jobs, right? And as you can see, the name there is Circuit Capital. And basically this job is not really on the semiconductor industry, but it does use your digital design skills. So it requires you to apply your digital design skills in the financial industry. So a brief description of the job would be that these companies would have automated trading algorithms, right, which they work by basically running extremely fast ahead of the market. And that's why it's called high frequency trading, right? And so basically because they need these trading algorithms to run so fast, so they require it to be implemented on actual hardware, which happens to be like FPGAs. Okay, so maybe let's look at, in my company, how the first 5 years of a digital design engineer work. come in as what we call a level 1 engineer. Other companies would, they have various terms for it, like junior engineer, associate engineer, engineer 1. So typically, you get hired into this role without needing any experience. Though sometimes if you have, let's say, 1 year of experience, working experience, you'll also be hired into this level. But just to point out, not having working experience doesn't mean having no experience. Because typically companies will not hire you if you have never touched very long. So your job responsibilities would be typically working on a single project, right? And within that you'll be responsible for, let's say, a small work. The expectation is that you'll be able to use the EDA tools, right? And you'll be able to run scripts for those tools that have been provided to you. And of course, usually you'll be under close supervision from, let's say, a senior engineer. But from time to time, you'll be required to assist trainees. And trainees would be, in some companies like my company, we do take in sometimes fresh grads who don't really have any relevant experience. So they will typically take 3 to 6 months to train up. So about 2 years after you start as a level 1 engineer, typically you move to a level 2. Some places call this just engineer, or mid-level engineer, or engineer 2, for example. If you were to be hired into a level 2, usually you take about, they will require you to have, let's say, 2+ years of experience. And as I mentioned, if you have a master's, typically you can be hired into this level. You would, on the job, you'd still be working on a single project. But now you are responsible for more blocks, right? Or maybe more complex blocks. By this time, you're expected to be familiar with the tools that you're using. Right? You're not asking your supervisor every time how to do something. And typically, you're also expected to be able to kind of modify the scripts. Right? You still require some supervision, but not that much. And by now, you'll be expected to assist those who are like 1 level below. Let's say another 3 years on from level 2 is when typically people reach level 3. So typically in the industry it's called a senior engineer or senior engineer 1, for example. To be hired into this level, as we kind of saw this now, requires about 4+ years. Yeah. So by now, your project management skills are expected to be at a level where you can actually be involved in multiple ongoing projects at the same time. And within each project, your technical skills are supposed to be good enough for you to be responsible for up to major subsystem level. By now, you are also supposed to be an expert with the tools, right? You've been using them for years and years. And by now, you'll be the one expected to create the scripts that are being used by the lower level engineers. And again, now you'll be the one who is actually providing the supervision to the L1s and L2s, and you assist them in their daily stuff. So that would be a typical 5-year career plan. Right? Okay, so if everything that I said kind of interests you, you're interested in pursuing this digital design career, concretely speaking, what are the next steps that you can take to move into this career? So what I'm going to do is show the posting for entry-level RTL designer that my company has posted on my careers feature, right? And I'll walk you through it. So firstly, this will be like the headline, right? So as you can see, it's a campus hire, so like hiring fresh grads. So this is actually the salary range for our starting fresh grads. This is like the monthly basic. So on top of this, actually we offer AWS, if you know what it is. Another is called 13 month. And also on top of that is a bonus as well. So indicatively something like 1 month bonus at least. I'm going to reference a figure which some of you all might be familiar with. So this actually figures from the 2021 graduate employment survey. Some of you might be familiar with that. So basically what it does is it shows the median and mean monthly incomes or salaries for recent graduates. So this one happens before 2021. For bachelors of EE, mean basic monthly is about 4.2. For computer engineering, 5.3. So the reason I bring it up is to reference that our salary range actually falls, pretty much nicely at those two levels. So just as a reference. Okay, so let's move on to some of the requirements for the job. So, as I mentioned, typically you require a bachelor's of engineering. Here we're being more general, but for NUS it would be like EE, ECE, CG. Okay. And it's a bit small, but here it says that no work experience required. However, relevant training and internships are preferred. Okay. I will talk more about this point later on. So here are the details of the job. So job description, the requirements for the candidate, and also preferred knowledge. It's a bit small, but so first point I want to make is that you guys being here in this module, CG3207, is actually a very good start on working towards a digital design career. So for example, you guys have already doing hands-on with let's say Verilog or VHDL this time, right? You all are doing already implementation of digital circuits, right? And you guys have experience doing your test benches, checking your designs. Also, you all have some ability, right, to read architectural specifications, like the ARM specifications, stuff like that. And also, you all have some idea of what we call PPA, so power performance area trade-offs. So for example, if you wanted your circuit to run faster, what do you do? You pipeline it, for example, right? Or you do parallel processing. So stuff like that. So trading off performance for area, for example. So that is the starting point. How do you build on that? So listed here would be basically a concentration or major in IC design. But for NUS terms, because we don't really have a major for that, right? So what it would mean is that you would move on to take higher level modules. And here I listed some, but I'm not saying you have to take all of them, right? Just some of them. And these might not be all the modules. For those, you have to check if your academic advisor or something like that, or maybe a prof. But 4218 under graduate, right? And 4415, 4434, and maybe even like master level modules, 5518. And these are all good modules that you can use to build up your experience in doing digital design. So as mentioned, FYPs and internships are another very good way to progress down this career, towards this career, right? And it's also in the FYPs and internships that you will be gaining some of the preferred knowledge for the job. So it could be things like industry protocols. For example, XC, DisplayPort, HDMI, Ethernet. So for example, in your FYP or your internships, if you get a chance to work on some of these protocols, that's a very good thing to have. Another thing that is good would be design techniques. For example, you might be doing FYP on, say, low power, right, or reset flows, or you might be using clock domain crossing in your internship. So these are also very good techniques to have, because these are definitely things that you will have to use on the job. And lastly would be proficiency in the scripting language. Right? So as I kind of alluded to previously in the 5-year plan, a very important thing for engineers to progress would be your scripting skills, which is another thing you can work on in your internship section. And lastly, in a more general sense, if you are interested in a digital design career, you should definitely try to keep up to date with the industry. You can do this in a couple of ways. So for example, checking various job portals, right, to kind of see what jobs are out there, what the job descriptions are like, and also definitely do reading up on industry blogs and news. And with that, I think I've come to the end of the first section, and probably we have some time for Q&A. Yes, we have about 10-15 minutes. Yeah, so before that, so just again, I want to mention about this contact email. So, after today, if you want to ask me more questions about anything I covered today. For example, you want to do an FYP or internship with my company, or even if you need some kind of career advice or maybe some help checking your CV or something like that. Or let's say you've been reading job descriptions and maybe you don't understand some parts of it, please feel free to reach out to me at this email. Alright, and now I open the floor to questions about the first section.
Yeah, there's a new Masters in CG program, right? I wonder what's it about.
New masters in CG.
Sorry?
Yeah,
the
the
new masters in
CG, yeah.
Yes.
Yeah.
It has just started.
Yeah.
Starting this August. Yeah.
Oh, it just started.
Yeah.
Oh. Oh, sorry, it's not relevant to the. Right.
No, it has some hardware focus for sure. Yes.
Oh.
There are 3 tracks. One is about hardware systems. The second one is about networks. The third one is AI and machine learning. If I recall that.
So you're involved in it also.
Okay, any other questions? You ask anything. Doesn't have to be what I presented. Maybe just something I didn't cover maybe, or some question you always have about semiconductor industry or yeah.
Okay, you mentioned that like in your opinion in the digital design field postgraduate degree is one as important.
Yeah.
Could you elaborate on that a bit? Like do you think like a master's is maybe useful but maybe a PhD not so much, or is there like depend a little bit on the job?
Sure. So let me address the question from say 2 directions. So firstly, from a top-down direction, if we were to look at the management teams of companies like let's say Intel, AMD, so IC design companies, right? You typically find that the engineering positions, so like VP of various engineering groups, or even the CTO, you'd be surprised that actually the number of PhD holders in those technical top positions is not that many. Many of them tend to be master's holders, like they've completed up to a master's degree, and you might even find 1 or 2 like bachelor holders. Yeah. So we can see that it is definitely not the case where you need to have a PhD or to rise all the way to the top of the company. And so from a bottom-up kind of approach, if you go through the job portals and you look for the requirements for various jobs, most of the time what you will find, they will say bachelor's/masters. So the point being that as long as you have at least a bachelor's, you are free to apply for a job. That is not to say that if you have a master's, you will be given the same salary as a bachelor's, of course. But it means that it's not a cut-off or a requirement for you to have a master's. And a PhD is even more rare. Most of the time, IC design jobs, digital IC design jobs, will not be requiring a PhD. And also typically, in those job applications, they will state something like bachelor's plus 5 years for a senior engineer position, for example, or master's plus 3 years, something like that. Typically, a master seems to confer a 2-year discount on the years of experience required. We can understand this by the fact that digital design is a very engineering-focused field. It's all about your experience in doing certain things. There is not much of the exploratory or research aspect to it. So therefore, like further studies tends not to be, because those are too specialized, right? They tend not to be so required and useful. So that is what I meant by postgrad confers a small advantage. Yes. Correct. We are headquartered in Silicon Valley, Milpitas, California. Yeah. It's basically founded by some of the industry veterans in the semiconductor industry. No. So we have basically 4 sites currently. So the first one is in Silicon Valley, Milpitas. Second one in India, third one in Philippines, Manila, 4th one here. And by end of year, there will be one in Amsterdam as well.
Can I ask another question? Firstly,
Wait, just hold one sec. Does anyone else have a question? Okay, go ahead.
okay, so two questions. Like, were you from NOC before? And secondly, also for hardware, right? Like, because I was in the ECE career fair earlier this year, they say for example some companies like Razer, they would prefer people with experience in hardware. You know, like it's if you're fresh grad, it's hard to get into hardware jobs.
Okay, so let me take the first part of the question first. So NOC I actually didn't go for NOC. As I understand it, NOC is geared more towards entrepreneurship, and if you wanted to do your own startup, for example, you would go there. But if you're going to an established industry, going to a company, being employed by a company, typically NOC is not the most productive use of your time. If you're planning to be employed by a big company. Second part of the question, so I think we need to look at the term what hardware means. Typically, if you search jobs, right, and you type hardware, it covers a broad scope, but very often it refers to things like PCB level design, right? So when they say a hardware engineer, they're talking about someone who can do PCB level design. Sometimes, but not very often, they are talking about IC design, but it's not common. So I hope that answers your question. Any other questions? Okay. Yeah, so I guess if there are no other questions, we can probably take a 15 minutes break. And then after the break, I'll be giving a brief sharing about cache coherence protocols, and in particular, what I use on the job to make my designs. Okay, so carry on. So let's say we have this system, we can call it a system on chip, or just a system. We are having multiple processors, right? Different kinds of processors. And of course, these processors have to draw their data from somewhere. So let's say it's the main memory, right? So basically, I'm sure all of us understand that a processor is taking instructions and operating on data. If we want high performance processing, what can we do? Well, you probably have covered already. There are a couple of ways, right? Two of those ways would be multiprocessor and memory hierarchy. Multiprocessor, what does that mean? Basically, it means that we have more than one processor working on a set of instructions, so we can actually run some of those instructions in parallel. Memory hierarchy means that instead of fetching the data to be operated on all the way from a main memory, which might be very far away, which might also be very slow, we can actually store some of the data which we think we will use, or which the processor thinks will be used, in nearby smaller and faster memories. Typically, we call those the caches. Right? And so in the diagram there, you can see so each processor has a cache, and here's the main memory. And also sometimes we have, so hierarchy means that we have different levels. Sometimes there will be caches in between the on-processor cache and the main memory. So we call this L2, L3 caches. The term is not important, it's just a general idea. So an issue arises when we have caches which are within the processors containing data. How do we ensure that the data is not actually conflicted with other caches? That is where we need a cache coherence protocol. Cache coherence protocol basically says that it's a way to allow various system components to have private caches which store memory data, right? While ensuring, importantly, it ensures that all caches contain the correct data value, i.e. there are no conflicting data values. Typically in industry, there are two ways to do it. One is called directory based, and one is called snoop based. Snoop based is what we'll be looking at today. So snoop based basically means that the various operations by the processors will be snooped or monitored by a central controller, which will then take the necessary steps to perform the cache converts. We'll look more into detail later. Now I'd just like to mention, for example, in a typical system in industry, we don't have just one person or one team building the entire system. It's not possible. Right? We might have multiple processors being built by different teams. And let's say even in this system, the memory controller might actually be an IP that comes from an external vendor. So clearly we need some way to ensure that all of these various components in the system can work together, that they are compatible together. And this is the reason why we have things called industry standards. Okay? So I'm going to talk about some industry standards next. And it's from a company which all of you should be very familiar with. It's called ARM. So ARM is basically a company that does architectures. It gives various architectures, right? One of the architectures it does is processor architectures, which you guys are familiar with. But another kind is also called system architectures. It is talking about how should we, what are a set of rules, right, by which we can build a system. One of the things under the system architectures that ARM does is called AMBA, or AMBA for short. It stands for Advanced Microcontroller Bus Architecture. So what it is, it's an architecture, right, a specification that talks about how the system's various components should be connected, right? And because these AMBA standards are free to use and they're also openly available, that is why they have become an industry standard. Basically, everyone uses them. So the IP vendors will be using the AMBA standards. The teams within the companies also using AMBA standards, and that is how we ensure compatibility. There are 5 key AMBA specifications. So we first look at the bottom 3. Basically, these bottom 3 deal with communication of components within non-coherent systems, meaning that the components in the system don't actually have private caches, private memories. Okay, and basically from APB to AHB to AXI, these are just evolutions of the standard, giving more and more powerful features. But what we're interested today would be the top 2 specifications called CHI and ACE, which are basically dealing with how the components in a cache coherent system will communicate. Because now we have the additional requirement that we have private caches within the components and we need to be not conflicted. The reason that I'm sharing this, right, is actually because in my current work, I'm actually working on the IP that is using these cache coherent protocols. So before we start into the details, let's have a look at how we will represent the cache moving forward. We can think of the cache simply as an array, right? Each element of the array we will call a cache line. Typically, a cache line has several parameters. One would be the address. What address is this? This is the memory address that this data is a copy of, right? Because remember, all these cache lines are actually copies of certain locations in the memory, right? So the address is where the data is located in the main memory. Of course, there are various ways to map this address to the main memory address, but I'm sure in your lectures you have already covered that, so I'm not going to. Data value is, of course, self-explanatory. It is the value of the data at a particular address. The more important thing to talk about is the state, and this is actually the state of the cache line. Right? I'll go more into that later. Last thing to note is the 2 terms called load and store. So what is load? Okay, so both load and store are actually terms for the processor's interaction with the cache. So importantly to note, these are private transactions. The only 2 parties involved is the cache and the processor. So it's not visible to the rest of the system. So load is when some cache line, right, some particular value at some particular address is being placed into the cache. So basically it was not existing in the cache previously, and we load the value into the cache. Store is referring to when an existing line in the cache has its data value modified. So the processor does some operation, modifies the value of the cache line. This is called a store. It's important because later on we're talking about read and writes, where read and writes are actually system communications, okay? But load and store are private between the cache and the processor. Now let's talk about cache state. So the ACE specification gives us 5 different cache states to work with based on 3 parameters. Firstly, let's talk about invalid and valid. Invalid basically means that for all intents and purposes, this cache line doesn't exist in the cache. So as you all might be aware, when it comes to memories, there is no real concept of discarding the memory. We just overwrite it, or we just say it doesn't exist. But physically, it's still there, right? So invalid is a way of saying that do not use this cache line. Okay. So when a processor tries to access a cache line which has a state of invalid, we basically call this a cache miss, and it will lead to a loading of this particular cache line. Right? So for example, if the processor wanted to access the data at address 0000, oh, and by the way, these values, the 16-bit address and the 32-bit data value, is just for demonstration purposes. Okay, it's not really what you see in a real system. So if the processor wanted to access the data value at address 0000, but however, we find that the cache state is invalid, so then the processor will generate basically a load, right? So opposite from invalid is valid, and under valid, then we have the 4 different states. So firstly, let's look at unique and shared. So when we say a cache line is unique, this means that this cache line is not found in any other caches in the system. Conversely, if a cache line is shared, it means that this cache line might be in other caches in the system. This is important because to avoid conflicts between the caches, a processor cannot store to a cache line which is not unique. If a cache line exists in more than one cache, the processor cannot store to it, because then that will cause a conflict. In terms of dirty and clean, dirty basically indicates that this particular cache line is not the same as the value in the main memory. It means that it has been modified. And it means that at some point, eventually, this new updated value must be returned to the main memory. Okay. So that's for cache and cache state. Let's look at the control system that we're going to be using for looking at request transactions. You can think of the requester, and these are terms from the CA transfer. So a requester, you can think of it something like a master. So in the system, a processor will be a requester. A requester will generate requests to read and write data, which will then need to be satisfied by the subordinate. And so these transactions will be passed through the ICN, also known as the interconnect. In the interconnect, there will be an important node called the home node. Home node is basically the one that is doing the snooping and ensuring that the cache memory protocol is correct. Yeah. Second thing to note is what are the communication channels between the requesters, the subordinates, and the interconnect. So the spec basically, the specification, basically gives us 4 types of channels, and each channel is like a bus, a collection of signals that transfers a certain type of packet. So for example, we have request packets, response packets, data packets, and snoop packets. Built on top of the idea of the channels is the transactions. So a transaction is a particularly defined sequence of packets, right? That will be required to run in a certain order to fulfill the transaction. Right? So we have read transactions, dataless transactions, write transactions, and these are actually all initiated by the requester. We also have snoop transactions, and snoop transactions are initiated by the home node. Okay. So let's look at our first transaction. So to orient you, in the center will be our example system. On the left hand side is requester 1's cache representation. On the other side is requester 2's cache representation. So let's look at the read in the case where the requester wants to, or the requester gets this memory, cache line from main memory. So as we see, an address 0000 in main memory, we have this particular data value. So let's say requester 1 wants to load this particular address. How would it go about it? So it will generate a request called read shed. And so this is the particular name for this request. This particular request in the CHI spec, right? It's called a read shed. It generates this request and it's picked up by a home node. So typically the home node will be aware of which caches contain which cache lines. In this case, it knows that no other cache in the system contains this line. So it will send the request on to the subordinate, who will then fetch the data and it will transfer back to the requester. And so then requester 1 can load the value to its cache. Okay? We note here that in this case, the state of this cache line will be UC. UC meaning unique clean. Unique because no other cache has this particular line. Clean because this is the same data value as in main memory. It has not been modified. So, what about the case in which we do not fetch the cache line from main memory, but we fetch it from a peer cache, which means from another requester? So, in this example, so requester 1 has this particular line in this cache, right? And let's say requester 2 also wants a cache line with the same address. So requester 2 will again generate a read shed request. But this time, home has been monitoring the transactions in the system, and it knows that, oh, okay, so requester 1 cache actually contains this cache line. So again, going back to the principles of memory hierarchy, to make it faster, right, it will not fetch the data from main memory, but instead it will fetch it from the tier cache. So what it will do is generate a sloop request known as the sloop shed forward, okay, which goes to requester 1. It's basically saying, asking requester 1 to provide the cache line at this particular address. So requester 1 will provide this particular cache line. Notice that when it does so, it has to change the cache line state to SC, standing for shared clean. Because now it knows that another cache in the system is going to have this cache line. So that's why it's shared. So the data will go to requester 2, and after loading, so this will be requester 2's cache. Note that again, the state here has to be SC, shared clean. So that's the read transactions. Let's talk about write transactions. So, write, and we'll look at it in 2 steps. So let's assume that our system starts with this particular cache states. Okay, so in specifically, both requester 1 and 2's cache contain the data at address 5400. Here we will note that this data, right, we can see main memory, this particular value, but in the caches it is a different value. In this case, one of the caches must have this cache line in a perfect state. Yes? So one will have it in SD. In this case, it just happens to be requester 2, and requester 1 has it in SC state. So requester 2 is going to write this cache line back to main memory. How does it go about doing that? So firstly, it will generate a write back request. So home will pick it up, and if this write transaction can go through, home will basically send a response. And specifically, it is a response with a combined request. So home will actually send a request back to requester 2 for the data at this particular cache line. So after that, what is requester 2 going to do? So requester 2 will send the particular cache line to the interconnect. And note that when it does so, it must change the cache line state to invalid. This is a specification for, this is just a part of the specification. So then the data makes its way to the subordinate, and you can see that main memory will get updated. Okay, so that was the write transactions. Now let's look at what dataless transactions mean. So a dataless transaction is one which doesn't actually involve transfer of data or from the data. It is basically a way where requesters can manage each other's cache. So remember that I said that before storing to a cache line, a master must make sure that the cache line is in a unique state. You cannot store to a cache line which is in a shared state. So let's say requester 1 has this particular cache line, 5400. It wants to update its value, it wants to store to it. However, it's in a shared state. So it must perform a dataless transaction, right? In this particular case, it will issue a clean, unique request to the home. And home, so home has been keeping track of the transactions. It knows that requester 2 actually has this line in the cache. So it will send a snoop request to requester 2, saying that so it's called a snoop clean invalid request. So upon receiving a snoop clean invalid, requester 2 will take a look at that particular cache line. Upon realizing that it is shared dirty, it realizes that it needs to invalidate this cache line. But remember, before we remove the cache line, because it's dirty, it will need to be returned. So let's say the write happens as according to what we saw in the previous slide. So we will end up with this particular state. So now cache line at requester 2 is in the invalid state, and main memory has been updated. So home can then send a response back to requester 1 saying that okay, the dataless clean unique transaction has been completed. And then requester 1 can then go ahead and update, store to this particular cache line. So note that now requester 1 can actually change the cache state of this particular line to unique dirty, right? Because after the dataless transaction, it knows that no other cache has this line, and also it has modified it, so unique. Okay, so yeah, I believe that is my brief explanation of how cache coherence transactions occur in in what you might see in an industry system, basically. So basically, I just hope to give you all some kind of idea about cache coherence systems and how cache lines look like, how data will be transferred around. Because as I understand, you all kind of touch cache coherence a little bit, but you all don't really go into so much detail. Okay, so yeah, I think that brings us to the end of the lecture. Do you guys have any questions about cache coherence? No questions? Yes.
Yeah, can I ask, like, for the previous slide you mentioned that the requester 2's cache line was dirty, even though its data didn't change. I think that.
Is that what I said?
Yeah.
Yeah. No, so this is just an example starting state of the system. So for purposes of the example, I'm going to say that in this case, requester 2, which is receiving the clean unique, request. The clean unique state has it in a dirty state. If it was in a clean state, then this example would be just completed without the other transactions. I just wanted to show an example of when a requester receives a clean unique state, if it has the cache line in a dirty state, what it has to do.
So normally it will be in the soup receipt. Then it's transferred from requester to cache.
No. Okay, so I go back again. So So here I'm explaining about dataless transactions. And a dataless transaction will be used by one requester to manage the caches of other requesters. A typical use case is when the requester that's doing the dataless transaction wants to store to a particular cache line. When it sees that this particular cache line is in a shared state, it has to first issue the dataless transaction called clean to ensure that all other caches in the system have invalidated their copies of this cache line before it can proceed with the store that it has to do.
Okay, thank you.
Did I see a question from this side? No? So, no questions means either I explain really well or I totally didn't explain clearly. Anyone want to feedback which one is it? Can you? Is it? It's good to know.
We don't even know what we don't know this one.
Okay. Yeah, so, but as I mentioned, this particular cache coherent protocols, AC and CHI, are actually what I've been studying, to do the design that I've been tasked to do. Right? So, the project I'm working on is called Network on Chip. So, which is basically the interconnect portion, right, of the. So, the design that I'm doing is actually the interconnect portion of the system. And so the interconnect has to handle cache coherent components. Right? So I have to study the protocols like ACE and CHI to be able to do my design. And so again, I would like to repeat that the process of digital IC design is like that. You look at the specification that you need to implement, you study it, you make sure you know it, translate it into your RTL design, and you test it. So again, it's really similar to what you guys are actually doing. Okay, so yeah, I guess today will be ending early then. Yeah.
Okay, once again, thanks a lot for attending and thanks for sitting through the whole session. And once again, let us thank Mr. Tim for taking his time to come all the way here and deliver this two-part lecture, which I'm sure was quite enlightening for you, right? Many of you had doubts regarding, what you will end up doing when you end up in the, or if you end up in the digital IC design industry, and I hope hearing it from the horse's mouth would have clarified quite a few of your doubts, and you hopefully have a better picture at this point. Yeah? And also the topic on cache coherence is pretty important. Some of it is already covered in this module, and I do talk about what is cache looping, but basically in a very brief manner in the last chapter. Yeah, when we talk about multiprocessor systems where this whole requirement to have cache coherence is even more important and a lot more challenging as compared to single processor systems where it's a lot more straightforward. Yeah. Okay, so once again, thanks everyone, and good night. By the way, I had forgotten to mention earlier, Hoi Annie is also actually working in the IC design industry, but she is doing analog design in MediaTek, which I'm sure you must have heard of. So yeah, see you all next week, and please be reminded that there is a quiz next week at around the same time as we had our quiz the previous time, okay, around 7:15, 7:30. Those who are in Zoom, do you have any doubts or anything that you need to discuss with the speaker, Mr. Kim? Okay, if you don't, I guess I'll close the session.